Hello students, in the previous session we studied about calculation of mean deviation about mean. In this session we shall look into the calculation of mean deviation about median. The process of finding the mean deviation about median for a continuous frequency distribution is similar to as we did for the mean deviation about the mean. The only difference lies in the replacement of the mean by the median. While taking deviations, let us recall the process of finding median for continuous frequency distribution. The data is first arranged in ascending order. Then the median of continuous frequency distribution is obtained by first identifying the class in which the median lies, that is the median class, and then by applying the formula of median, that is L plus n upon 2 minus C upon f into h, where median class is the class interval whose cumulative frequency is just greater than or equal to n upon 2 and n is the sum of the frequencies. Here L, f, h and c are respectively the lower limit, the frequency, the width of the median class, and C the cumulative frequency of the class just preceding the median class. After finding the median, the absolute values of the deviations of midpoints xi of each class from the median, that is absolute value of xi minus m, are obtained. Then mean deviation for median is calculated as 1 upon n into summation I ranging from 1 to n fi into absolute value of xi minus m. Now, let us solve an example to understand this. Calculate the mean deviation about median for the following data. We have class ranging from 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50 and 50 to 60. Corresponding frequencies are 6, 7, 15, 16, 4 and 2. Now look into the solution. The class interval containing n upon 2th or 25th item is lying between 20 to 30. Therefore, median class is equal to 20 to 30. We know that median is equal to L plus n upon 2 minus C upon f into h. We also note that L here is 20, cumulative frequency is 13, f is 15, h is 10 and n is 50. Using the formula, median can be calculated as 20 plus 25 minus 13 upon 15 into 10, that is equal to 20 plus 8, that is 28. Now, we shall prepare a table having the following columns: first representing the classes, second representing the frequency, third showing the cumulative frequencies, fourth showing the midpoints xi, and fifth showing the absolute value of xi minus median, and next is the product of fi into absolute value of xi minus median. Now, cumulative frequencies, as you know, can be calculated as first 6, next 6 plus 7 gives us 13, 13 plus 15 that is 28, 28 plus 16 is 44 and so on. Now, the midpoints of the classes are taken as 0 plus 10 upon 2 that is 5, 10 plus 20 upon 2 that is 15 and so on. Now, by taking the difference of xi minus median, we get the following entries here. Then we calculate the product of frequencies and the difference of xi minus median. So, we get here and we find out the total of these, that is 508 in this case. So, using the formula for mean deviation for median, we have 1 upon n into summation I ranging from 1 to n fi into xi minus m. Substituting the values, we get 1 upon 50 into 508, that is 10.16. Therefore, the mean deviation is 10.16. Now, students, let us study about variance and standard deviation. Recall that while calculating mean deviation about mean or median, the absolute values of the deviations were taken. The absolute values were taken to give meaning to the mean deviation, otherwise the deviations may cancel among themselves. Therefore, the mean deviation about the mean is not very scientific. Thus, in many cases, mean deviation may give unsatisfactory results. Also, mean deviation is calculated on the basis of absolute values of the deviations and therefore, cannot be subjected to further algebraic treatment. This implies that we must have some other measures of dispersion. Let us discuss the limitations of mean deviation. In a series where the degree of variability is very high, the median is not a representative central tendency. Thus, the mean deviation about median calculated for such series cannot be fully relied. The sum of the deviations from the mean, minus sign is ignored, is more than sum of the deviations from median. Another way to overcome the difficulty which arose due to the sign of deviations is to take squares of all the deviations. Obviously, all these squares of deviations are non-negative. Let x1, x2, x3, xn be n observations and x bar be their mean. Then xi minus x bar whole square plus x2 minus x bar whole square plus so on plus xn minus x bar whole square is equal to summation I ranging from 1 to n xi minus x bar whole square. If the sum is 0, then each xi minus x bar has to be 0. This implies that there is no dispersion at all, as all observations are equal to the mean x bar. If summation I ranging from 1 to n xi minus x bar whole square is small, this indicates that the observations x1, x2, x3 so on xn are close to the mean x bar and therefore, there is a lower degree of dispersion. On the contrary, if this sum is large, there is a higher degree of dispersion of the observations from the mean x bar. Can we thus say that the summation I varying from 1 to n xi minus x bar whole square is a reasonable indicator of the degree of dispersion or scatter? Let us take the set A of 6 observations, namely 5, 15, 25, 35, 45 and 55. The mean of the observations is x bar, that is equal to 30. The sum of the squares of deviations from x bar for this set is summation I varying from 1 to n xi minus x bar whole square is equal to 5 minus 30 whole square plus 15 minus 30 whole square plus 25 minus 30 whole square and so on, can be calculated as 625 plus 225 plus 25 plus 25 plus 225 plus 625, that gives us 1750. Now, let us consider another set B of 31 observations, namely 15, 16, 17, 18, 19, 20, 21, 22, 23, so on till 45. The mean of these observations is y bar is equal to 30. Note that both the sets A and B of observations have a mean of 30. Now, the sum of the squares of deviations of observations for set B from the mean y is given by summation I varying from 1 to 31 yi minus y bar whole square can be calculated as 15 minus 30 whole square plus 16 minus 30 whole square and so on for all the values as 45 minus 30 whole square. This on calculation gives us minus 15 whole square plus minus 14 whole square and similarly 14 square plus 15 square. that can be solved as 2 into 15 square plus 14 square plus so on plus 1 square. That gives us 2 into 15 plus 1 into 30 plus 1 upon 6. This on calculation can be obtained as 5 into 16 into 31, that gives 2480. Because sum of the squares of first n natural numbers is equal to n into n plus 1 into 2n plus 1 upon 6. Here n is equal to 15. If summation I varying from 1 to n xi minus x bar whole square is simply our measure of dispersion or scatter about mean, we will tend to say that the set A of 6 observations has a lesser dispersion about the mean than the set B of 31 observations. Even though the observations in set A are more scattered from the mean, the range of the deviations being from minus 25 to 25 than in the set B, where the range of the deviations is from minus 15 to 15. This is clear from the following diagram. Look here, for set A we have the values on the number line as 5, 15, 25, 35, 45 and 55. The mean here is 30. Now, for set B we have the values ranging between 50 to 45. Here the mean again is 30. Thus, we can say that the sum of the squares of deviations from the mean is not a proper measure of dispersion. To overcome this difficulty, we take the mean of the squares of the deviations, that is, we take 1 upon n into summation I varying from 1 to n xi minus x bar whole square. In case of set A, we have mean is equal to 1 upon 6 into 1750. That gives us 291.67, and in case of the set B, it is 1 upon 31 into 2480, that gives us 80. This indicates that the scatter or dispersion is more in set A than the scatter or dispersion in set B. This conforms with the geometrical representation of the two sets. Thus, we can take 1 upon n into summation xi minus x bar whole square as a quantity which leads to a proper measure of dispersion. This number, that is mean of the squares of the deviations from the mean, is called the variance, and it is denoted by sigma square. Therefore, the variance of n observations x1, x2 so on xn is given by sigma square is equal to 1 upon n into summation I varying from 1 to n xi minus x bar the whole square. So, students, today we introduce ourselves to standard deviation and variance of the data. We shall continue with some examples to understand this. Thank you.